Welcome to Science, everybody. Hanging in there? Good job. Keep it up. This is a lot, no doubt. Let's talk wind and pressure systems. It's a general rule in nature that things don't like, nature doesn't like, quote unquote, that's not really a thing, but nature doesn't like an imbalance. Nature doesn't like there to be a different concentration of things in two different areas. The way I always explain this is if I took the whole entire 10th grade and crammed them into this classroom, what would it be like in here? Just what is it like? Uncomfortable, noisy, too many people, we're bumping into each other, we're probably getting irritated, probably getting hot, everything else, right? That would be like a high concentration of people in this room. So if I threw the doors open, like just naturally, if I didn't even say anything and just threw the doors open, what would people like naturally do? They would leave. They would get out of here. They would go from an area of higher concentration to an area of lower concentration because that is what naturally happens to everything. If you do this with air molecules, you concentrate them somewhere and they're not somewhere else, they're going to move in response to this. If you do this to like salts and sugars in your bloodstream, there's going to be diffusion to balance out that. It's how you stay alive, honestly. Nature doesn't like this imbalance. Things in nature fix that, right? So going back to the people example, if everybody kind of left this room and spaced out, maybe some people stayed, some people went to the hallway, some people went to other rooms. If we all got about the same distance from each other, there'd be a balance, there'd be an equilibrium. But if we all went into Hefty's room, then it would just be a high pressure situation over there and people would leave. So it's always this balance of like things get wadded up and mashed up and in high concentration, and then they attempt to leave that to go towards low concentration. Tons of examples of it. An air compressor is a machine, a little tiny motor that just jams air molecules into a metal cylinder. That's what all that noise is as those things get off, right? As those things go off. It's jamming and jamming and jamming more and more air into there. It's creating high pressure inside the canister. So you grab the hose and you click that little button at the end of it, and it just opens it up. And what does air do in response? It leaves. It leaves the high pressure situation and goes towards low pressure situations. In nature, that still happens. There's high and low pressure systems all over the place because of all the weather stuff we've been talking about. And wind is going to be a reaction of the difference between those two. The air molecules themselves don't want to be in that high pressure situation, don't want to be in that high pressure situation. They leave and they go towards the lower pressure. So let's look at what happens with pressure systems in a very simplified sense. If we do this as a side view, which just like above is going to say like, okay, here's the ground. So here's a house, here's a tree. We're still talking like that magical side view that would be really hard to do scale wise. But if I could look at the atmosphere from the side and see it, high pressure would be a situation where the winds want to go away from it. Low pressure would be a situation where the winds want to go towards it. And this, I know I say this a lot, but this is one of the primary things that drives weather, is this air moving from high to low. So in side view, again, we'll do one last house and tree. My houses and trees are getting rougher and rougher as the videos go on. Don't overthink it. These arrows just represent wind. It's wind. It's air moving away from the highs. This is wind. Air moving towards the lows. Okay? Now, something funky does happen. I left a lot of space here. As the air blows towards that low, I'll do it on the bottom of the camera here, as it's going towards and towards and towards and towards, eventually, as it hits, it's got nowhere to go, but where? Where's the only place left? It all jams in, and it's going to go up. And here we go again. As I promised, you'd have to say it multiple times, air rises. And what happens when air rises? I should have just heard you say it expands and cools. And then all that other stuff. Hits the dew point, condensation, relative humidity is 100%, air is saturated, and we get to a point where we form clouds. So you can count on low pressure systems being cloudy in general because as the air goes towards it, it gets sucked up in that rising air, creates clouds. And why? Because of the cooling. Expands and cools. It's got to be like, got to be in your head. Expands and cools, expands and cools, expands and cools. When air rises, it expands and cools. Because as you cool, and this is like where all these lessons start to pile up and hopefully make more sense. If you're going at this disjointed and jumping around assignments, it's going to make less sense, which is unfortunate. So please go in order. If you did the whole relative humidity dew point lab and you did the idea, why is it so dry indoors? It's dry indoors because we, with heaters, make the temperature go up. We make a big difference between temperature and dew points. This is like the opposite. This is drop the temperature closer to the dew point, which creates humidity. It takes that water that's already in the air and makes it a higher relative humidity. Air rises and form clouds. Over here in the high pressure system, okay, it's spreading out on Earth's surface, but in response, it's going to drop down into that high from the upper atmosphere, which means air sinks. And when it sinks, it compresses and warms. So now you're doing what we do indoors with heat. You're making the temperature go up, keeping the dew point the same. You're making the difference between temperature and dew point greater and greater and greater. So this is like a natural system for making it low humidity. It'll be clear. High pressure systems. If you're hoping for a clear day for some outdoor events, you look at a map. If you see a big H, you're in good luck. In fact, we'll write kind of as a quick, this is a silly little rhyme that helps some people. High and dry versus, come on, computer, low and lousy. Why? The sinking air compresses and warms, dries us out. The rising air expands and cools, creates humidity, creates clouds. Okay. What about map view? So this is looking from the side out of the atmosphere. What if I could get into like a spaceship and look down on these systems? And then we'll go to a website and actually try to look at some real live ones right now. Well, we said that the wind's got to spread away from the high. So what you got to picture is from my eyeball, winds are going straight down to that H, hitting Earth's surface and spreading out. Winds go away from a high. But now we got to go and bring our friend the Coriolis Effect to the party. Don't draw these arrows I'm about to draw. If the Earth were not spinning, air would just move directly away from the highs in the shortest path possible. Just let's get out of here, right? But we do have a spinning Earth. And if you remember the light bit of Coriolis stuff we talked about with Foucault's pendulum, with other ideas, here in the northern hemisphere, the paths get bent towards the right. 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 And if you don't believe me that that one is turning to the right, flip your paper over and you're going to see that, yes, that arrow is indeed turning right as it goes forward. So high pressure systems, the meat and potatoes that we would have to fight through the lab is that air moves away. And then with it, there's a circulation around it, which is clockwise around the high. Away and clockwise for high pressure systems. Low pressure systems, we're going to be the opposite, right? I'm going to draw this with a slight technical inaccuracy. For those of you that go study this in college, you can come back and tell me I'm wrong here. But I'm doing it for sake of simplicity. That we're going towards the low and turning right. We're going towards the low and turning right. We're going towards the low and turning right. What this leads to, lows suck everything towards it, right? And then if I'm looking at the surface of the Earth, they'd be coming right up at me off the Earth and forming clouds, covering up this whole low. They also are like going to be pulling cold air masses towards them from the north and pulling warm air masses up from them from the south. And that is what makes these things so interesting. Like a meteorologist is going to be bored by a high. It's high, it's dry, it's clear. My job's done. They like lows because they like doing their job, because they create clouds on their own. They pull cold air down, which creates a cold front and creates those clouds. They pull warm air up, which creates a warm front, which creates those clouds. This is where the action is. And by action, I'm generally meaning clouds and precipitation. So again, amateur meteorologist looking at a weather map saying, what's the weather going to be like? If you see a big L and you're hoping to do something nice outside, you might be out of luck. Low and lousy, right? Again, for the meat and potatoes, what we got to know right there, air moves towards, and there is a counter clockwise flow around the low pressure system. Okay, let's look for some in real life here on Earth. If you type in Earth null school, Nullschool, into the Googles, this first website that comes up, that's what it's called, Earth Null School. Very cool to play with. What it shows us are the wind patterns on the planet right now. So I see a nice flow right here. What is this guy going to be? It's going around counterclockwise. It's pulling air generally towards it. This front right here is a bit of a mess. We'll look at that in a sec. But that is a good example right there of a low pressure system that's blown off into the ocean. Unless you're sailing out there, no concerns. Let's look for a high. I would say right here, dominating the Atlantic Eastern Seaboard is a larger high. See, other ones are kind of going away from it, and there's a clockwise flow. Those are kind of the two good ones right now. We've got a kind of messy one up here in Hudson Bay. Bit of a low there. And again, real life meteorology gets complicated, right? When you get multiples together, how you figure that out, it gets tricky. Let's go way over here. There you go. Ooh, it's a strong one. And look at how far it's pulling air up from the south, like from Hawaii all the way up here, which is not too far off the islands here off of Alaska, the Aleutian Islands. So these systems can be responsible for really sucking massive amounts of air. I would not want to be out here in this weather right now, out in the ocean. This line right here is a very nicely formed cold front. So look at cold air whooshes down from way up north, gets to there. That line is the front. That's as far as the cold air is making it right now. Warm air making its way up that way. There's a high right there, moving away and moving clockwise. All right, play with that website a little bit if you'd like. But if you got the notes, I think we've done a good job. Keep up the fight, everybody. I do appreciate it. So long for now.